Hello and welcome to our practical on specific heat capacity. Make sure to put on your lab coat and safety goggles, as we're ready to transform our theoretical understanding into a hands-on investigation. In our previous sessions, we've delved into various types of energy, such as potential, kinetic, and thermal energy. You're already familiar with the concept of a specific heat capacity, which tells us how much energy is needed to raise the temperature of 1 kilogram of a material by 1 degree Celsius. We've also discussed how different materials require different amounts of energy to experience the same temperature change, with materials like water needing quite a lot, while metals often require much less. Before we get started, let's briefly outline the importance of this practical. Firstly, understanding specific heat capacity is essential in the fields of engineering and material science. Engineers, for instance, rely on this knowledge to design systems capable of efficiently managing thermal energy. Whether it's developing components for automotive engines that need to effectively dissipate heat, or creating electronic devices that must maintain optimal temperatures to function correctly, the specific heat capacity of materials plays a pivotal role. This understanding is thus crucial in designing safer, more efficient, and longer-lasting products and systems. Moreover, in our quest to tackle global warming and focus on energy sustainability, specific heat capacity emerges as a key factor. Thermal energy storage and management are critically important for renewable energy systems, including solar power and geothermal energy. Materials with high specific heat capacities are particularly valuable because they can store large amounts of thermal energy, which can then be released when needed. This capacity is crucial for creating sustainable solutions for energy storage and improving the energy efficiency of buildings. On to the practical. Let's start by gathering our materials. Sam, what do we need?
So for this practical, we need a 1 kilogram aluminium block, power supply, an ammeter, a voltmeter, an immersion heater, a thermometer, some oil, some cotton wool, and finally, a lab book.
By exploring the experiments investigating specific heat capacity, you are not only enhancing your grasp of core thermal physics concepts, but also recognizing their importance in real-world applications. Now that we're ready, let's get started. We'll begin by taking a solid block of aluminium, which has 2 neatly drilled holes on its top surface. These holes are specifically designed to accommodate an immersion heater and a thermometer. We'll also make sure to note the mass of our block. In this case, it's 1 kilogram. Next, carefully insert the immersion heater into the larger of the 2 holes. Ensure it fits snugly to maximize heat transfer. Then place a thermometer in the other hole to accurately measure the temperature of the metal. We'll then add a couple drops of oil around the thermometer to ensure it is surrounded by hot material and can accurately inform us of the temperature of the aluminium block. Next, let's fully insulate the metal by wrapping it with loose cotton wool. Before applying any heat, record the initial temperature of the metal from the thermometer. This baseline is crucial for calculating the temperature change later on. Now, connect the immersion heater to a power supply, an ammeter and a voltmeter. The diagram in the top right shows you how you can draw this setup in your lab book. The voltmeter and ammeter will allow us to calculate the electrical energy supplied to the heater, which will subsequently be used to heat the metal block. Ensure all connections are secure and double-check that the power supply is set to the correct voltage and current settings. Switch on the power supply to start the experiment and begin recording the time. As the immersion heater begins to transfer energy to the metal block, keep a close eye on the thermometer. Once 10 minutes have passed, note the reading on the voltmeter and ammeter. These values represent the energy supplied to the heater during the experiment. Now you can promptly switch off the power supply. Note that the temperature of the metal may continue to rise slightly even after switching off the power, so ensure to watch the thermometer closely and note the highest point it reaches in our lab books. In your lab books, draw a table recording the ammeter reading, the voltmeter reading, the initial temperature, and the final temperature. With this information, we can begin to calculate the specific heat capacity of the aluminium block. Recall that the equation for change in thermal energy is mass multiplied by specific heat capacity multiplied by temperature change. As we can identify the values for change in thermal energy mass and temperature change, we can rearrange this equation to find the specific heat capacity. Let's break this down carefully. Firstly, we know that the mass of the aluminium block was 1 kilogram. Secondly, we can calculate the change in temperature by subtracting the initial temperature, which in this case was 16 degrees Celsius, from the final temperature, which was 37 degrees Celsius. This gives us a temperature change of 21 degrees Celsius. Next, we need to calculate the amount of energy that was transferred to the aluminium block. This calculation is slightly more complicated, so let's break it down slowly. First, take a look at these two equations from our electricity module. Don't worry if these don't look too familiar, as they are explained in greater detail in other lessons. In these equations, we can see that energy transferred equals power multiplied by time, and that power equals potential difference, also known as voltage, multiplied by current. As power is present in both equations, we can combine them together. Because energy transferred equals power multiplied by time, and power equals potential difference multiplied by current, we can replace the power in the first equation with potential difference multiplied by current to give us the equation energy transferred equals potential difference multiplied by current multiplied by time. We can now use this new equation to calculate the total amount of thermal energy that was transferred to the aluminium block. We know that the time elapsed during the experiment was 10 minutes, which is 600 seconds. We also know that the potential difference was 10.6 volts, as this is recorded in our table. Finally, we know that the current, as measured by the ammeter, was 3.5 amperes. Using this information, we can calculate that the total energy transferred was 10.6 multiplied by 3.5 multiplied by 600, which gives us a total of 22,260 joules. Therefore, we know three elements of our initial equation. The change in energy was 22,260 joules, the mass was 1 kilogram, and the change in temperature was 21 degrees Celsius. With this data, we can return to our original equation. Let's plug our values into the equation to find specific heat capacity. This gives us 22,260 joules equals 1 kilogram multiplied by C multiplied by 21. Now, let's rearrange the equation to find our unknown, or C. This gives us 22,260 divided by 1 multiplied by 21 equals C. Overall, this gives us a specific heat capacity value of 1,060 joules per kilogram per degree Celsius. This means that our experiment found that it takes 1060 joules to increase the temperature of 1 kilogram of aluminium by 1 degree Celsius. This is actually above the specific heat capacity of aluminium, which is 900 joules per kilogram per degree Celsius. How can we explain this? Well, all experiments involve some level of error due to imprecise measurements or uncontrollable variables. In this case, not all the heat from the immersion heater is used to warm the aluminium block. Some of the heat escapes to the surroundings. As a result, more energy is transferred than what is required to heat the block alone, leading to a calculated specific heat capacity that is higher than the actual value for aluminium. In today's practical, we investigated the specific heat capacity of various materials. Specifically, we used the formula energy transferred equals mass times specific heat capacity times change in temperature to calculate the specific heat capacity, highlighting the essential relationship between the energy supplied, the mass of the material, and the resulting temperature change. This practical deepened our understanding of how different materials respond to heating and how energy is stored and transferred. Thank you for joining us in the lab today. We look forward to seeing you around here again.